stresses are, you will not be able to get interlaminar stresses accurately using the displacement-based finite element. If you use displacement-based finite element for laminates, then the interlaminar stresses what you get between the interlayer of the lamina, the stresses will not be accurate. For that, interlaminar stresses are included as a degree of freedom. Then the stresses evaluated at the interlaminar will be more accurate. Otherwise, one has to use very, very refined mesh and then get the stresses. The other way is use the three-dimensional equilibrium equations and then evaluate. That is another way of doing it. Here I am presenting a formulation where interlaminar stresses are included as degree of freedom. So this is a general XYZ coordinate system, and laminas are stacked like this. This is one of the lamina with the angle theta, and this is a some sample three-dimensional element. Okay, fine. Now the finite element formulation I will principle of virtual work I will present for the this case where interlaminar stresses are included as degrees of freedom. Fine. Now we know this is a compliance matrix. Here it is given as yes. Actually, so far I was talking about compliance in terms of C. Now k equal to 1 to n, where n is the number of layers considered, and integration of Vk is the kth layer considered, and its dvk is the volume integration. Now, the principle of virtual work delta epsilon transpose sigma, this is the usual principle of virtual work, has been considered, and you have to use the appropriate matrices, appropriate stress strain relations at the ith layer, and you have to sum them up to get the total stiffness of the laminate. Now, I want the formulation is such where I wanted to include the interlaminar stresses as degrees of freedom. What has been done is delta sigma Ez transpose, where sigma Ez is a vector containing sigma Z, tau xz, and tau yz, and it is multiplied with epsilon Z minus S bar sigma. Epsilon Z consists of epsilon Z, gamma xz, and gamma yz. Gamma xz, gamma yz, and gamma xz minus S bar sigma, where S bar sigma is all the six component. From this, you include only the three equation. This will be 3 by 6. This will be 6 by 1. So that is being used here. Minus. So that is 0. That equation I am constraining. I am multiplying with sigma z because that is the right counterpart. When you generate the energy, you should multiply with the right counterpart. Otherwise, you will not get the right energy. So delta sigma z, this side is sigma z. Okay, now what has been done is sigma z, tau x z, tau y z also been included as degrees of freedom. Now we will see how the whole thing is going to get converted into finite element form, the stiffness and how it is going to change. Now, this is my epsilon x usual strain and I have included sigma ij, tau xz, and tau z as degrees of freedom. I cannot violate what is given. I have no right to change the mathematics, but I have appended with the extra zeros, thereby I'm not violating the actual mathematics. So it is epsilon x equal to dou u by dou x only, epsilon y equal to dou v by dou y only, and this is not going to change anything. This adding extra is not, this equation is valid. Now here u, v, w, sigma z, tau x, tau y z, they are all my relation that is expressed in terms of safe function matrix, and ui, vi, wi, sigma zi, tau x zi, tau y zi are the nodal variable right now. This is the safe function matrix I told you. This is the nodal displacement vector. Now in the displacement vector I have included sigma j, tau x z, and tau y z also degrees of freedom. Now epsilon is equal to b into q. My b is going to be, it has to come from this, and sigma is equal to d b into q. So I have to adjust such a way that b it gets properly expanded and d remains the same. And sigma z is also required because sigma z is part of the equation. Now sigma z equal to n sigma into q. Q is, I told you, Q is containing sigma z, tau xz, and tau yz. And when I write sigma z, there should not be any displacement part. So this satisfies the requirement. And when you multiply, you will end up with sigma z equal to ni sigma zi only, tau x z, tau y. That way it has been arranged. And further, this S bar sigma is split into two, containing normal stress as well as interlaminar stress. Interlaminar stresses normally it is told as sigma z, tau x z, and tau y z only. So sigma x again it is written in terms of sigma x tau xy transpose d bar b into q. Actually, why? Because I have to use only those relations only. D bar is that reduced D matrix. It is because I am now talking about only six out of six, only three stress term. Then when you come use the D matrix, you have to use only that 3 by 6 equations, and then that way it has been arranged. Then S bar sigma equal to, substitute here, it ends up like this. This relation already written. This is S2. So finally, S bar sigma is expressed in terms of nodal displacement vector. Then this equation is substituted into the main equation, and thereby B transpose dB. This is the extra term that gets along with the stiffness matrix that causes that provides the interlaminar stresses as degrees of freedom. And here where interlaminar stresses as a degree of freedom, those locations are applied as 0 only. Only loads is applied only corresponding to the displacement positions. So wherever tau xz and tau yz positions are, they are made zeros in the force vector term. Okay, now being told this, I like to show some results. At this level, any question is there, I can answer also. How this interlaminar that has been included as degrees of freedom in the formulation. Any clarification required, I can answer also. Basically, this brings in the whatever is required. Okay, if no questions, I take it as understood. So now, is this slide is clear?
Yes, sir.
Okay.
Yes.
Actually, now that how this formulation works, we have to solve some problem and see also. So here 090, 90, 0, 90, 0, 0, 90. It is a symmetric laminate and uniform stress being applied in the epsilon x direction. And how this method works, we wanted to see. So in one case, it has been messed with a single element with 16 elements along it, and in other case 28 28 by 2, 16 by 1. The whole thing has been assembled with only one brick element here, 2, and as it goes towards the boundary, it has been discretized with more number of elements. So and here one extra advantage what one can get is one can even suppress the sigma z tau x z tau y z as 0 also. It is possible. That is the boundary stress is 0, and here also tau y z is 0. That is possible to apply here. And okay, and this has been solved, and stresses are okay. 0, 90, 90, 0. This is how the stress variations sigma z epsilon 0 through y by b. Y is, yeah, along y. This is how the stress variation is. This is the sigma z stress variation. That is for, I think there is some problem. This is tau y z stress variation. And and the other thing is we have solved other problem also where the load varies sinusoidally. Actually, it is we have to go in very detail to explain the problem itself. That's why I'm rushing through. This to show, these are all some. This is the variation. Normal shear stress. Tau exigent variation. And this is tau exigent for different combinations of 0, 90, 90, 0, like that. Actually, three cases have been considered. Okay, here the point is when you want to solve, when you want to get the accurate estimate of interlaminar stresses, use mixed formulation instead of displacement based formulation. That can be taken as a, that is the message, take home message. So you will not get, by using a displacement based finite element, you will not get sigma z, tau x z, tau v z accurate. And why that is very much essential? Because they contribute to the delamination. So if you want to estimate where delamination will occur or not, for that these stresses to be predicted accurately, then you estimate whether the stresses are beyond the, it is bonding, debonding is going to happen or not. For that purpose, it has been suggested to use mixed finite element formulation. Okay, this is the you can take this is the message. Fine. Okay, this message is clear. Hello.
Yes, sir, clear, sir.
Yeah, actually, you use interlaminar stresses as a degree of freedom by in a finite element formulation. This is one of the way, but there are other methods also there how to include. So you take this message and you take a reference or a literature and you use your own way of arriving. You can even find a formulation by yourself also, not necessarily this way. And there are other ways also being shown in the literature. Okay, fine. Actually, so far, the telemetric clocking where it has been used for incompressible material, where volume before and after remains the same due to loading. And these materials are being used in mainly in our in rocket industry in solid propellant rocket motors. Solid propellant rocket motors are viscoelastic material. So when I say viscoelastic, it says viscous plus elastic. There is some portions which is elastic which comes back, and there is some portion because if you think of spring and dash part are together, it is there. When you apply a load, it will not come back immediately. It takes some time to come back to its original. So that time delay is known as viscoelastic behavior. So that viscoelastic represent the viscoelastic behavior in solid propellant and other materials. It has been expressed in terms of Prony series. Prony series is this is the this is the expression relative uh, relaxation modulus is actually this is E infinity, that is the equilibrium modulus. When you plot this Young's modulus versus time, it will be high initially. As time goes, it will reach an equilibrium, and that value will be very low. And that modulus is equilibrium modulus. And other things, because it is decaying exponentially, and this is the expression. And this can be solved as a time marching itself. That is one way of solving. And the other one is direct direct method. Where, this is proposed by Safari. What he said was, instead of solving it time with every time you use this expression, then what he said is you take the Laplace transform of this expression and multiply with s and put s equal to 1 over 2t at the instant of time where you want the solution. That will give the viscoelastic effect, that history, the solution, what has happened previously, the impact of that will happen on the next step. Instead, if this is being used, it is going to give a close results. Otherwise, what you solve using time marching scheme. That is the method proposed by Safari. So if you take the Laplace transform of this, it is nothing but this expression only, and this is EFS equal to S into this, and substitute here, you will get the solution. And shall I show some results what we have obtained using scholastic method? Actually, these are all the solid propellant rocket motors, and for solid propellant we have used the Safari method what I have told you, and this method has been used with constrained variation problem. As I told you, I'll show that equation and then further I will come to that. But you will connect. So I was telling you this is the expression for strain and the stress component, strain component. And this is the constraint epsilon b equal to minus 3 alpha delta Tp by k that has been imposed as a constraint to this. And here the what I told you the viscoelastic where Young's modulus varies with exponentially with time. So that has been solved using the Safari procedure where Laplace transform of relaxation modulus is taken and then multiplied with S, and 1 by in place of S 1 by 2t is substituted where the instant of time where I am interested in this viscoelastic solution. So this element, using this element we have developed using this method plane strain, axis symmetry and three-dimensional elements. And this element has been well tested with literature problems. I'll show you some of the results. Yeah, actually we have tested, and it was this work was published in International Journal of Pressure Vessels and Piping. We have taken single element and uniform stress was applied on either end, and the moment was applied, and uniform shear was applied. And we are able to get the matching results with the closed form results what we have derived also. And then it was tested with patch test also. Patch test is one where you take a patch of elements and then you apply uniform stress so that the uniform stress is predicted throughout the body. So this is the patch of elements considered to perform the patch test, and uniform stress was applied in these two phases, and it has passed the patch test also. And this is Cook's membrane problem was solved, and these are all the results. 23.90 is the result provided in literature, and 23.8362 we are able to get the V displacement. So these are all some of the problems we have solved using this constraint variation problem. And this is to show that this element works well. Finally, this is being used in solid rocket motor cases, and results obtained using the present method has been compared with the commercially available software called Mark. Just I'll show you one case study results, how it matches with the more precise. Actually, this is a high performance solid rocket motor casing where this is the casing. This is made of composite and this is the solid propellant. The pressure is applied internally because it is that is the kind of pressure it experiences at the time of ignition, and what maximum pressure it is going to experience throughout the burning, that has been applied here and then tested whether any debonding or testing for structural integrity. That's why it's called integral integrity testing. And the results comparison have been there somewhere. 1 minute, I will show you the results. Actually, I was having it. Corrected thesis. Any question is there, you can ask me also. Anybody? Hello?
Yeah, anybody want to ask any question, please?
Anybody want to ask any questions?
Hello. Hello. Good afternoon, sir.
Yeah,
Hello.
yeah, please.
Sir, sir, please little explain the safe function in FEM, sir. Safe
Which
function about.
which one? I
Sir,
didn't get
safe
you.
function.
Safe
Hello,
function.
sir.
Okay.
Yes, sir. Yes, sir. In FEM.
Okay. Okay. I'll explain. I'm looking for that result. Okay. We are able to match good results with Mark software. And okay, this is the viscoelastic solution method. And so before going into the next one, since one of the person asked safe function, actually it is defines the shape of the field variable, how the field variable varies within the element. Shape function or interpolation function, both are same. To explain, I will consider a simple bar element. Bar element, it has 2 degrees of freedom. It only deforms in axial direction only. So if you take an arbitrary element, you will have 2 displacements, that is u1 and u2. Okay, it is 2 noded bar element. Am I conveying?
Yes, sir.
1 minute, I will take the right appropriate so that it will be. Okay, you take this is the 2 noded bar element. Okay, and x equal to n1 x1 x equal to n1 x1 plus n2 x2, u equal to n1 u1 plus n2 u2. where n1 equal to 1 minus r by 2, n2 equal to 1 plus r by 2. Okay, how it has been arrived, or the properties of safe functions are such it is 1 at its own node and 0 elsewhere. For example, if you take n1 equal to 1 minus r by 2, this r varies from minus 1 to 1. If you substitute r equal to minus 1 here, you will get n1 as 1. And if you substitute r equal to 1, where n1 is 0, that satisfies, safe function should satisfy that conditions also. Should satisfy, it is 1 at its own node and 0 elsewhere. Similarly, for n2, if you consider, if you put r equal to minus 1 here, this becomes 0. And if you put r equal to 1, this becomes 1. So if u equal to n1 u1 plus n2 u2, when you consider this, and u1 and u2 are nodal displacements, if you want to get displacement at any point within the element, substitute at that point. R goes from minus 1 to 1. Okay. And anywhere in between. Here it is minus 1, here it is 1. If you want at 0.5, you substitute 0.5 and get, and this dictates the how the shape field variable shaping, what kind of shape it takes within the element. It will take only linear shape. It will be u1 at this point and it will be 0 here, and u2 at this point it will be 0 here. So that's how the safe function term has come. And hello, the person asked question, is it conveying? Hello,
Yes, sir.
are you convinced?
Yes, sir. Yes, sir. Thank you, sir.
Okay. And it can be how this function has been arrived also. You use this function. 1 minute, I will find some other. And hello, the person who has asked question, I suggest you to read a book by Chandrapatla and Balgundu, Introduction to Finite Element Method. And one more book also is recently, it is going to be published, the book written by BSSC team. It will come soon. You can take that book also and refer. Okay.
Okay, sir.
Shall I continue with my?
Sir, any other book recommended for introductory FEM?
Eh?
Any other book is recommended for introductory FEM?
No, introductory. Do you have that book? Have you referred a book by Chandrapatla and Palagunda?
Any other?
Any other? You read R.D. Cook. R.D. Cook.
RD Cook. Okay.
Hmm.
Th- Thank you,
Okay.
sir.
Okay. 1 minute. I will drink some water. Hello.
Yes, sir.
Okay. I was talking about static viscoelastic analysis, where the properties changes with time. Actually, this material is such, when you subject it to the loading, it will be very stiff at the beginning, and then it is slowly expand. Then it stays there after some time. That means how the other material behaves. Apply the load, it deforms, then it comes back to its origin. That is elastic. So this one, it is showing very stiff behavior in the beginning. Then, as the same load is applied, it deforms further and further, and then somewhere it reaches the equilibrium. That is the way this viscoelastic material behaves. Now, when you consider the same material for dynamic loading, what happens? The dynamic viscoelastic material subject to dynamic loading exhibits complex form, which is a function of frequency. Actually, when it is subjected to viscoelastic material, when it is subjected to time dependent loading, it should damping should happen. So damping, it should damp out, and then it should come to the equilibrium, static equilibrium position. So what is the way it has been done is, now the viscoelastic material has been subjected to dynamic condition, and whose properties are evaluated as a complex function of frequency. The real part represents the elastic energy, that is stored energy. The imaginary part refers to dissipation energy. It gets into two components. The machine used is dynamic mechanical analyzer. Once you use the dynamic mechanical analyzer, you will get E dash and E double dash. E dash is the stored energy, E double dash is the dissipative energy due to dissipation. So, using that, when your elastic property itself is complex, when you put it in the governing equation, you will get the stiffness in the form of real and complex, consisting of viscoelastic materials subjected to transient. Don't, I'm not talking about transient loads. When it's subjected to dynamic loads, not necessarily transient, it can be harmonic load also. In that case, it gets into complex form. And the, if you are applying harmonic loading, I will show the equation, then I will come. Actually, this is the way the equation gets into. This is the stiffness matrix, where it consists of, it become complex. Actually, this formulation is shown for Herman formulation, Herman or constant variational formulation. So this is the complex part. This and this gets into complex. Okay, this is the mechanical load. This is the thermal load. Now, when your load is harmonic, F sine omega t or F cos omega t or F e to the power I omega t, then what happens is this equation falls into the same domain. Same domain means it is in frequency domain. This left side equation is in frequency domain, and applied load also in frequency domain. Then this equation can be solved directly and you can get the solutions. Supposing the applied load is in time domain. When the applied load is in time domain, what happens is this this is in frequency domain, applied load is in time domain. So it become a problem. You cannot solve it. You have to bring it uniformity in the structural equations, the equilibrium equations. For that purpose, the applied transient load, which is in time domain, that has been transformed to frequency domain through Fourier transform. Once you transform into Fourier transform, then both the equations happens to be in the same domain. Then you solve the solution in frequency domain and get the solutions in frequency domain and take the inverse Fourier transform that will predict the damping present in the system. So I'll show you some of the problem, how the damping here Poisson's ratio, material properties. I'll show you the problem, then I will come to this. This is a problem one where propellant, liner, and casings are there. Actually, this has been solved as a static problem first, where Poisson's ratio is 0.499 and all taken. And the same load, internal pressure, is applied in these forms. Actually, up to this it is 0. Then this is a pulse load, rectangular pulse. Rectangular pulse is applied, then brought back to 0. Then once again rectangular pulse loads are applied. This is one type of load. The other one is rectangular pulse load is applied and brought to 0. This is another type of loading. The same pressure loading is applied in this form. Then the trapezium pulse load is applied, and this is the sinusoidal load. And this is the general transient. Now we will see how the structure responds to these loadings. Okay, problem one is this, and this is here and here viscoelastic properties are assumed. This is a casing, this is steel. This is a representative of solid propellant motor case. The propellant liner, which is made of rubber, and casing. The other problem is this is simply supported beam where the hash line shown is made of viscoelastic material and top and bottom are made of steel. Now, how the response should be for this semi supported beam for this loading. It is a pulse load, suddenly applied pulse load, then brought back to 0. Then once again load is applied. You see the response here. This up to this it is 0. Then due to the suddenly applied load, it goes back, and it has been duration is sufficiently enough to die out because of viscoelastic material is there. The time duration of the application of the load that brings it to the static equilibrium position. This is due to the damping, it damps out and it reaches the static equilibrium position. Then once again it was dropped to 0. Because it was being dropped to 0, the dynamic happens with respect to zero position because there is no load. Then it comes back to zero position. Then once again load is applied, equilibrium, the vibration happens with respect to static equilibrium position. Then once again it was dropped. So this is to show that how the viscoelastic problem has been solved and why this, how it is damped out. The next case where pulse load is applied and dropped, then it has to vibrate with respect to static equilibrium position and it has come back to, once it is dropped, its equilibrium position is zero, mean position is zero position, so it vibrates with respect to that and it stops there. This is a trapezium pulse load, how it responds. And the other load is this sinusoidal load where it and it has been brought to zero. Here also it comes back to zero equilibrium position. Here some transient loads are applied and it is stopped somewhere and so it will stop at equilibrium position will be in with respect to this loading. Whatever, when you apply this load, whatever the beam reflect, that should be the equilibrium position. This is for sinusoidal loading. Hello? Hello?
Yes, sir.
So the viscoelastic, how it behaves, is it clear?
Anybody want to ask any question, please? Participant. So I think it is okay.
Okay.
Yes.
Actually, you here take home is whenever viscoelastic material, when you solve for dynamics, you will get the properties in the form of complex. One is elastic energy, another is dissipative energy. So that way the equations are formed, and when you solve it for dynamic loading, because of the dissipation energy also present in the system get damped out. So that is the message in this. And when you apply a harmonic load, you can solve it directly when you express the elastic property in the form of stored and dissipative energy. And when you apply a load which is a time domain, you have to bring it into uniformity. For that, you have to transform the loading into the frequency domain and solve in frequency domain. And the solution you transform to the time domain to get the proper response. Okay, that is the whole content of this dynamic viscoelastic problem in nutshell. And now I will talk something about fluid structure interaction. As I told you, fluid structure interaction, we are using it in the case of contained liquid. The liquid tank contains the liquid, and one can use either finite element method or boundary element method to represent the fluid. One can use both finite element method for to represent both structure and fluid, or boundary element method for fluid and finite element method for structure. And I will give a general representation to fluid structure interaction problem. One is the structural domain is marked as omega s, and omega f is the fluid domain, and omega f0 is the free surface of the fluid, and delta omega s0 is the free surface of the structure. This is the interaction. The gamma is the interface between the fluid and structure. And the same equation, what we have derived, the body force equilibrium equation, gets in this form for dynamics, where dou squared u by dou t square rho s into dou squared u by dou t square. This is the second equilibrium equation, third equilibrium equation. This is the free surface equation. Corresponding to structure, and this is the wave equation which governs the fluid motion. And at the free surface of the fluid, tau p by normal derivative with respect to pressure is 0. So this can be written in global terms: dou p by dou x nxf, dou p by dou y nyf, dou p by dou z nzf equal to 0. This is same as dou p by dou n equal to 0. At the interface, dou p by dou n equal to minus rho f, the fluid density, into dou square un by dou t square. So that when you write in terms of components, it gets dou square u by dou t square. The same as it is dou p by dou n equal to minus rho f into dou square u normal by dou t square. That same thing has been expressed in this form. Okay, fine. Now, for incompressible fluid, what we are dealing is incompressible fluid, and the fluid is incompressible. The velocity in the fluid media, velocity of sound in the fluid media is very high. So 1 over c squared, the velocity of is very high. Velocity of the sound in incompressible fluid media is very high. So this term can be neglected. And now we want the equivalent finite element form. So how it is going to get? So we have seen the discretization of this whole thing already, how it gets into the finite element form. Now, in this case, how it is going to get? Because acceleration time is there, mass matrix will come, and this will contribute to the stiffness part. So final equation is structural mass into acceleration, structural stiffness into displacement is equal to Fp. This Fp is the force that is generated due to fluid pressure on the structure. You have a liquid contained in a container. The pressure that acts on the structure, cause of the force on the structure, that is called Fp. That can be conveniently written in terms of area matrix into P, area transpose matrix into P. Then the global equation of the discretized fluid domain, it gets into L. This is due to actually this also you will get one more term m m of p m of that mass due to the fluid contains the 1 over c squared term. This due to this term you will get mf, like ms you will get mf, and that becomes 0 for the incompressible fluid. So then you will end up with this equation only. At that the interface you will have area into acceleration term. Now you condense this pressure, you will get L inverse A into this acceleration term, and we have a pressure is written in terms of acceleration. This P you can substitute here, that's what I mean. Here P is there, no? This P, if you invert it, L inverse A will come. Then once you put it here for P, it is A transpose L inverse A with a negative symbol. So that part you can add it with the mass matrix. That is called added mass. That gets added to the structural mass. That will give how the structural characteristics, dynamic characteristics changes with respect to presence of the fluid. Hello?
Sir.
Am I there? All of you there?
Yes,
Okay.
sir. Yes, sir.
Yeah.
Okay. So this is a example. No, it is finally the take home is this is the structural portion, and you will get because of the fluid you will get a pressure on the you will get a force on the structure, and here you will get due to the interface you will get a matrix, and then that is being substituted back to the structural equation, and you will get added the mass get added due to the presence of the fluid. That changes the dynamic characteristics of the whole tank. It changes the uh, frequency and mode shifts. So this is a simple cylindrical tank where one end is open, another one is closed, and liquid is filled. And different T and different depth of fluid liquid filled, we have solved the problem, and it is a bottom fixed. This is a empty tank, and this is the result what we have obtained from our the formulation, present formulation. So these are all the results in comparison with the literature as well as present analysis. And and it was the tank was fully filled. So how the frequencies, and then this 1 3 means 1 along 1 and 3 along the circumference. 2 means you will have one mode in the along the length direction, one mode, and then 4 modes along the circumference. That is the meaning. So this is how the mode shapes are represented. So these are all the comparison results for this case. Okay, this is 50% filled, 70% filled case, and this is a sample liquid tank used in launch vehicle, where liquids are filled in both the tanks, and it has been studied for 4 different cases. Results has been compared with the non commercial code. Case 1 is where there is no liquid, and case 2 where liquids are filled in the bottom alone, emptied in the top, and third case is bottom alone, top alone, emptied in the bottom, and fully filled. How the results are comparing with Nostran software has been shown. So right now yeah, right now I have talked to you on fluid structure interaction, where how does the dynamic characteristics changes with respect to the presence of the fluid, dynamic characteristics of the structure. Next is slosh, axisymmetric tanks being considered for the study actually. Here in this case, the structure is assumed to be rigid, and how does the liquid behaves? That study is called slush, and this is being very essential for propulsion. And it has been assumed that frequency structural tank is very high compared to the frequency of liquid. And structure is assumed to be rigid. And studying the frequency of the liquid subjected to lateral motion is called Slosser analysis. The domain consists of liquid and boundaries of the liquid. That is the domain what we are considering. The boundaries of the liquid are container and free surface. Okay. Boundaries of the liquid are container and the free surface. We are not going to discretize the container at all. We only discretize the liquid in this case. The equation corresponding to the domain of the liquid and the boundaries of the liquid are considered for the present study. Most of the tanks that are used for launch vehicle are axisymmetric in general. Hence, finite element formulation for axisymmetry is considered for the present study. The results obtained for the circular cylindrical tank cylinder using present formulations presented. The motion of the liquid in an axisymmetric tank with rigid walls and horizontal ground motion is considered. Horizontal ground motion is considered. Displacement is assumed to be small. Linear theory is applicable. Here we are considering the fluid to be irrotational and incompressible, inviscid liquid. The functional equation governing liquid motion. This you can get it from this was taken from the literature. This is the functional for the liquid, and take a variation with respect to the field variable. So here phi I and VA are the field variables. Vx, phi is the velocity potential, Vx the velocity. Now, when you substitute this and take the variation with respect to model variable phi I and Vi, so you will end up with this set of equation. And for the present case, square matrix. Yeah, in the present case, V is assumed to be 0. We are interested in dynamic characteristics of the liquid only. So we have not considered the other part, like what we do for structural equation, where we wanted to study dynamic characterization. We'll equate it to 0 and solve it. The same way is also being considered. And you substitute for phi e to the power y omega t, and then you will end up in this kind of equation. This will give the mode shape of the liquid and the frequency. This is the free vibration of tank containing liquid reduces this form. Okay, for numerical study, is the tank considered H is 70, rho is 1 gram per cube, R0 equal to 111.5 cm. Elastic potential. Okay. This is the results we got compared to literature. This is the literature value. This is the experiment conducted, and this is another person who has studied, and this is our result. What we have got through this formulation, what I have presented. And this is the tank considered. Don't forget, this is, you forget this portion. This is the tank discretized with finite element, 4-nodal finite element. And this is the first mode where you see the liquid motion only. This is the second mode. This is the third mode, and whose frequencies are given in this. The first frequency, second mode frequency, and third mode frequency. Okay. Now, finite element method is used in the form of substructure or condensed form. Actually, you have a huge structure. This can be solved in terms of considering small substructure form. Actually, this is the whole structure. This has been considered as 4 substructures. And the advantage here is you can eliminate these equations, these nodes, and you will arrive at the interface nodes between the subdomains. This is substructure or subdomain method. So this has been discretized into 4 substructures. So when you consider this substructure 1, you eliminate the nodes which are interior to this substructure, and you will arrive at the nodes on this and stiffness corresponding to this. And when you consider 2, you will eliminate these nodes and you will end up with this. Similarly, you end up with this, and then these stiffness matrices are assembled and solved to get the nodal displacements of this. And using the eliminated equation, you can arrive at the interior of the subdomain or substructure. What is the and then you can evaluate the stresses and strains interior. What is the big advantage is this become parallelizable. This once you do this way, you can parallelize the code. You can solve this separately. You can solve this separately and arrive at the boundary interface nodal stiffness only. Similarly, interface nodal stiffness only you can solve it with some other. You can solve parallel. You don't have to wait for this other because these nodes has no relation to the other portion of the structure. So these can be eliminated. This can be eliminated simultaneously, and only what is required is it needs to be assembled at one place the interface matrices, and you can solve and get the interface variables. And once you get the interface variables, you can get back. You can supply to each of the subdomains these interface variables, and you can evaluate the nodal variables corresponding to the interior of the domain. And you can evaluate the derived quantities such as strains and stresses. That's called static substructure. Same thing is there for dynamic substructure. That's called Gray-Hampton method. Okay, this is to explain that whatever I was telling. We have domain 1, and like that you can get for different domains, and then you can assemble them for the 4 domains, and you can and the corresponding reduction when you apply the load also it should be properly reduced to this. Then you can solve them and you can get back that variable. So biggest advantage in this method is you can simultaneously solve. You don't have to wait. Every domain can be parallelly processed, and because nowadays computers are coming with multi-core, it can be used that technology. And substructure in this, anybody have any questions can be asked. Hello? Hello? Okay, I'll proceed then.
Yes,
Anybody can stop me also in between. If no questions are there, I will go ahead. Okay,
yes, sir.
fine.
Sure.
Okay. Next is substructure and dynamic analysis. Is similar to that. It can be static mode, and this is the static mode. Actually, I'll come to that. Actually, here the static mode and the scalar points that called scalar point. This is the Gray-Hampton matrix. So I think I will tell in nutshell what way it is going to help. actually. That is more important. In aircraft industry and in rocket industry, there are different groups are there. Wing group, fuselage group, like that different groups are there, and they can perform their dynamics part, and the interface matrices only they need to supply to get the dynamics characterization of the whole aircraft. For that, wing group is there. Wing group, everything it does itself, and then they will supply the interface matrices to a one team where they get interface matrices from different people, and they assemble and solve, and they will provide the mode shape of the whole interface portions. Then that will be supplied to the wing portions using the mode shape of the interface nodes. They can extract the mode shape of the wings, and this being used now in our applications where we have satellite modeling is satellite modeling is done at Bangalore Satellite Application Center. They study, they design, they do everything there, and then they will supply only the interface, the Gray-Bampton matrices corresponding to the interface nodes, where it has to be interfaced with the launch vehicle. That portion of the matrices being added, and then we study here the complete dynamic characterization of launch vehicle plus satellite. That, and then that will give the what otherwise the full thing is modeled. What otherwise you model launch vehicle plus satellite together, when you do the dynamic characterization, what frequency you will get and what mode shape you will get otherwise also by assembling the interface matrices alone with the launch vehicle, and then you will get the dynamic characterization. And the interface mode shapes are provided back to the satellite group, where they will study using this how the mode shapes are, that they will get the mode shapes, and frequencies anyway they will be having with them, and mode shapes it will be missing, because how the mode shapes are going to be when it has been assembled with the launch vehicle, that they will be missing. That information will be provided assembling the interface matrices and solving the whole launch vehicle, and interface mode shapes are provided back to them. They have the frequencies, and using this they can get the mode shapes also. So this is possible. So this way it is the each team can work separately without waiting for the other one. Design part they don't have to wait. Only the how the overall frequencies and these things has to come. One team will work. Okay. Now that I have covered most of the part. Before closing it, I will give some introduction to nonlinear also. Actually, when one has to go for nonlinear analysis, the basic question anybody like to know, actually whatever we are studying in small strain or small displacement or infinitesimal theory, the configuration, what we are considered for the study before and after loading, they are practically the same. It doesn't make much different from the original configuration. That's called infinitesimal theory. That means you have a configuration, you applied the load, and you plot the deformation and the undeformed one in one-to-one scale. You will not see any significant difference. They are practically the same. So that's where linear theory holds or infinitesimal theory holds. But when you plot in one-to-one scale, the initial configuration and the deformed configurations are significantly different, then nonlinearity comes into the picture. When the geometry is significantly different, that is geometric nonlinear. And when you see the stress-strain relation, where some portion between the stress-strain relation is linear, so that is the elastic theory applies. Once it crosses that stress level, it will not come back to its original position. There will be a permanent set. So there, in such locations, in such places, you have to use material nonlinear. If there are situations where both are significantly different, then you have to use combined material geometric nonlinear. The other nonlinear is contact nonlinear, where boundary changes during the deformation. So these are all the major zones where nonlinears are encountered. So these are all the different nonlinear analysis classification. Material nonlinear, infinitesimal, displacement and strains, stress relations is nonlinear. Stress strain relation is nonlinear. Displacement is infinitesimal. Material nonlinear only. This is called material nonlinear only. That means you are not considering the geometrical configuration is not significantly different from original, whereas stress strain relation goes into the nonlinearity. Large displacement, large rotation, but small strains. There are situations it goes to the large rotations, but strains are small. So the approach used is total Lagrangian or updated Lagrangian. Total Lagrangian is the approach where everything is referred to the original undeformed configuration. An updated Lagrangian, it is considered the previously deformed converged configuration is taken as a reference. It keeps moving. Whereas in total Lagrangian, whatever originally I have considered before loading, the same configuration has been considered till the end. And and this has been, I am bringing bringing this slide to give a exposure that such things are there being used, and such kind of deformation also happens the actual scenario. For that is the purpose of this slide, so that it is giving a know-how that you will be aware that in reality such things are also there and being used also. Large displacement, large rotation, and large strains. Used updated Lagrangian German formulation and total Lagrangian formulation. Parameters will be different actually. Once you go into nonlinear, there are so many strain measures and stress measures, and while forming the energy, you have to use the appropriate stress measures and strain measures to form the complementary to each other. Actually, you have one bucket where stresses are there, another bucket where strains are there. You should use the right pair while formulating. And contact analysis, change of boundary conditions during the deformation. Okay, I think this is only to show you that such things are there, and this is a simple way to explain linear elastic means what I mean. The, the displacements are small, and here stress strain relations are linear. You are always, it goes in the same form only. And this is called elastoplastic, where after that it takes a different slope. And once it go into this region, it will not come back to its original. It will come parallel to the elastic line. Material, this is called material nonlinear only. And this is the large rotation, large displacement. It goes. This is the original. This is a piece that has been picked up from the actual configuration. And after deformation, how it happens. Large displacement and large rotation, but small strains. Strains are small, but it undergoes large displacement and large rotation. And this is the large displacement, large rotation, and large strains. This is the contact nonlinear. Change in boundary. It, up to this, it will behave the one way, and once it touches this behavior changes. And I think for nonlinear analysis, the method used are mainly used are Newton-Raphson method. Newton-Raphson method, you don't have to be afraid. It is something what you have studied in your basic mathematics, where f of x is given in terms of cubic polynomial x cube, and using Newton-Raphson, you would have evaluated x. The same method being used, only thing it is, instead of one equation, you will have a system of simultaneous equation, and there you will get f dash of x, and here you will get stiffness matrix, tangent stiffness matrix. That's all the difference. And only thing you have to appropriately evaluate, and once you use, you will get a quadratic convergence. I think I will stop here. Any questions I like to answer for the rest of the time? Hello?
Participant can ask the question.
Any questions?
Participants, any question, please?
Any non-linear, any?
Yeah, sir, one question is popped out. Sir, how can FEM model for the interaction between fiber and matrix properties regarding stress concentration behavior of composites?
Between fiber and
Fiber and matrix properties regarding stress concentration behavior of composites.
okay.
I think probably he's asking about laminar composites and the stresses at the interfaces.
Yeah, yeah. Actually, what has been assumed in the laminated composites, what we are doing is it is properly. There are so many assumptions are made, and recently I have seen some of the publications exactly what he is asking for. This phase field method being used. How does between the fiber and matrix? I would suggest you refer a paper by one of the professor Singh we, from IIT Roorkee. He has used phase field method. How does those things varies also? He has considered by giving some crack or without that also he has studied. And hello,
Sir,
yeah. So he has modeled the fiber as well as the matrix in his formulation, and he has studied it exclusively by phase field method. Okay.
okay, Sunil Chaudhary, is it clear?
Yes, sir, it is clear, sir. And sir, I want to ask that how to predict the sir model, how to predict model accuracy if we model something about regarding this my question, then how can we predict model accuracy?
Hello, in between you are not audible. Hello.
Sunil, can you repeat your question, please?
Sir, how can we predict the model accuracy?
Model accuracy. Okay. Actually, normally what is being done is you will model something and then you refine the mesh and you go on refining the mesh, and then where the previous results and the present results matches, that has been taken as the means the results were correct. That is convergence study. And I would suggest the other one, it is the error estimation and adaptive meshing, where it is not necessary to that you go on refining and it will come to the convergence, but this it will reach some level of modeling, some level of finite element mesh, it stops there. And one more thing is model accuracy. When you ask, we are doing finite element itself because we don't know the results. We are not knowing the results beforehand. The cases where we know are the closed form solutions, which is known, and thereby for such problems we validate our method whether it is working or not, and afterwards whatever results you are getting through finite element, that has been accepted as a solution, and it is your duty to make the right kind of boundary condition, right loading, everything you should make it sure, and then you have to accept the results. Further, if you want to confirm, then experiment validation is the only thing which is left. Okay.
Okay, sir.
Sir, there is
Thank you, sir. Thank you, sir.
sir, there is another question by Shashank Shekhar Singh. Is it possible to analyze a rotor system, say turbine supported on roller general bearings, rotating in a given speed range using fist?
Using fist.
Yes, sir.
The fist, we don't have that capability. Actually, it is not available.
Okay, sir. So, any other question by any other participant, please?
Actually, there is a exclusively one subject is called rotordynamics, and it has to be that whirling and these things all comes. Whirling frequency where when it is when it is rotating at particular speed, it gets it mode shape and these things are different. That's the whirling